Welcome! In this session, we'll explore LeetCode problem number 889, construct binary tree from Preorder and Postorder Traversal. This problem challenges us to reconstruct a binary tree using two specific tree traversal outputs, Preorder and Postorder. It's a fantastic exercise to deepen your understanding of tree structures and recursion. Let's dive in. In this problem, we are tasked with reconstructing a binary tree from two traversal sequences, Preorder and Postorder. The Preorder traversal visits nodes in the order of root first, followed by the left subtree, and then the right subtree. On the other hand, Postorder traversal visits the left subtree first, then the right subtree, and finally the root. Given these two traversal arrays, our goal is to construct the original binary tree and return its root node. Importantly, we are guaranteed that the input represents a valid binary tree, which ensures that the reconstruction is always possible. Let's look at the first example to better understand the problem. Here, the given Preorder traversal is 1, 2, 4, 5, 3, 6, 7, and the Postorder traversal is 4, 5, 2, 6, 7, 3, 1. The binary tree constructed from these traversals has the root node as 1, with two main subtrees. The left subtree, rooted at 2, contains the nodes 4 and 5, while the right subtree, rooted at 3, contains the nodes 6 and 7. The Preorder traversal reflects this structure by visiting the root first, then the left subtree, and finally the right subtree. Similarly, the Postorder traversal confirms the structure by visiting the left subtree, then the right subtree, and ending with the root. This tree is fully reconstructed step by step using the traversal data. Now, consider the second example. Here, the Preorder traversal is 1, 2, 3, and the Postorder traversal is 3, 2, 1. In this case, the binary tree has a root node of 1, but the structure is different. The left child of the root is 2, and 2 itself has a right child, which is 3. This results in a tree where the nodes are arranged such that each subtree has only one child. The Preorder traversal confirms this by visiting the root first, then the left subtree, and finally its child. Similarly, the Postorder traversal confirms the structure by ending with the root, after visiting its subtrees. The problem also provides constraints to help guide your implementation. The length of the Preorder and Postorder arrays will always be the same, ranging from 1 to 30 elements. Additionally, all values in these arrays are distinct integers between 1 and 10,000. This ensures there are no duplicate node values in the tree. Some edge cases to consider include a single node tree, where both traversals are identical, and trees with only left or only right children. For example, a tree with only left children will have Preorder and Postorder traversals that appear mirrored, but the tree structure remains valid. These constraints and edge cases ensure that the problem can be solved within the given limits. By carefully following the constraints, analyzing the traversal patterns, and considering the provided examples, you can confidently construct the binary tree for any valid input. The examples demonstrate how the tree structure emerges from the traversal data, and the constraints ensure that the solution is computationally feasible. With this understanding, you are ready to implement and solve the problem. To tackle the problem of constructing a binary tree from Preorder and Postorder traversals, we first considered a brute force approach. The main idea here is to recursively build the tree by splitting the arrays into segments for the root, left subtree, and right subtree. The Preorder array helps identify the root as its first element, and the left child as the second element, while the Postorder array is used to determine the boundaries of the left and right subtrees. Specifically, we locate the left child, Preorder 1, in the Postorder array, which gives us the size of the left subtree. Recursively applying this process for the left and right subtrees allows us to build the entire tree. However, the major drawback is the inefficiency of repeatedly searching for elements in the Postorder array, which takes linear time for each search. This results in an overall time complexity of O(n) squared, in the worst case, making it impractical for larger trees. Although simple to understand, this approach does not scale well and inspired us to seek a more efficient solution. To address the inefficiency of the brute force approach, we turn to an optimized strategy that uses divide and conquer along with a hash map for constant time lookups. The intuition remains the same: the first element of the Preorder array is the root, and the second element represents the left child. However, instead of repeatedly searching for the left child's index in the postorder array, we pre-compute these indices using a hash map. This eliminates redundant searches and significantly improves efficiency. The process involves creating a helper function that uses pointers to track the segments of the preorder and postorder arrays as we recursively construct the tree. The base case is simple: when the segment is empty, we return none. For non-empty segments, we use the postorder index of preorder 1 to find the boundary of the left subtree and recursively construct the left and right subtrees. The hashmap construction requires O(n), and since the recursion traverses the tree in O(n), the overall time complexity is reduced to O(n). While this approach does require additional space for the hashmap, the trade-off is well worth it for the improved time efficiency. The chosen strategy for solving this problem is the divide-and-conquer approach with index mapping, as it offers the best balance between clarity and efficiency. By leveraging the hashmap to store postorder indices, we avoid redundant searches and ensure a linear time complexity. One key insight that simplifies this strategy is recognizing that the postorder index of the left child, preorder 1, defines the boundary for the left subtree. This eliminates unnecessary computations and makes the entire process more streamlined. The decision to adopt this approach was driven by its ability to handle large inputs efficiently, unlike the brute force method, which becomes prohibitively slow as the input size grows. With its combination of speed and manageable space overhead, this strategy provides an elegant and scalable solution to the problem. When comparing the two approaches, we can see clear trade-offs. The brute force method has a time complexity of O(n) squared, due to repeated searches within the postorder array, while its space complexity remains O(n). Its main advantage is simplicity, but it falls short for larger trees because of its inefficiency. On the other hand, the optimized strategy achieves O(n) time complexity by avoiding redundant searches and leveraging the hashmap, though it still requires O(n) space. This approach is both efficient and scalable, making it the better choice for this problem. The additional space required for the hashmap is a reasonable trade-off given the significant improvement in time efficiency. Overall, the chosen strategy ensures our solution is not only fast but also easy to understand and implement, making it ideal for a wide range of input sizes. In this problem, we are tasked with reconstructing a binary tree using its preorder and postorder traversals. Preorder traversal tells us the order in which nodes are visited in a root left-right sequence, while postorder traversal gives us the order in a left-right root sequence. The challenge is to deduce the structure of the tree using these two traversal orders. Now, let's break this down. In the preorder array, the very first element represents the root of the tree. Similarly, in the postorder array, the last element is guaranteed to be the root. A key insight here is that the second element in the preorder traversal represents the root of the left subtree. By locating this left subtree root in the postorder array, we can determine all the nodes that belong to the left subtree. With this foundation, we can recursively apply the same logic to construct both the left and right subtrees. This recursive structure is what allows us to rebuild the tree step by step. To implement the algorithm, we start with the base cases. If either the preorder or postorder array is empty, there's no tree to construct, so we return none. If there is only one element in the preorder array, it represents a single node tree, and we can return that node directly. Next, we focus on constructing the root. The first element from the preorder array becomes the root of the current subtree, so we create a tree node for it. To identify the left subtree, we use the second element of the preorder array, which is the root of the left subtree. By finding this element in the postorder array, we can determine the boundary of the left subtree. Let's call the number of nodes in the left subtree L. These nodes correspond to the range pre 1EL plus 1 in the preorder array and post L in the postorder array. With these boundaries identified, we make recursive calls, one for the left subtree using pre 1EL plus 1 and post L, and another for the right subtree using the remaining elements, pre L plus 1 and post L-1. Finally, we combine the constructed left and right subtrees by attaching them to the root node. Once the recursive calls are complete, we return the constructed root node, which now has its left and right subtrees attached. This completes the process of reconstructing the tree. The algorithm relies on the efficient divide-and-conquer principle, breaking the problem into smaller subproblems for the left and right subtrees. A critical step in this process is correctly identifying the boundary of the left subtree in the postorder traversal. This ensures that the nodes are partitioned accurately between the left and right subtrees. By leveraging array indices, the algorithm avoids redundant computation, making it highly efficient. The time complexity is O(n), as each node is processed exactly once, and the space complexity is O(h), where h is the height of the tree. The space complexity accounts for the recursive call stack, which is proportional to the height of the tree. To summarize, this algorithm effectively reconstructs the binary tree by combining divide and conquer with the properties of preorder and postorder traversals. Let's see how this algorithm works with an example. Suppose we have pre equals 1, 2, 4, 5, 3, 6, 7, and post equals 4, 5, 2, 6, 7, 3, 1. The root of the tree is 1, which is the first element in the preorder array. The next element in preorder, 2, is the root of the left subtree. By locating 2 in the postorder array, we determine that the left subtree consists of the nodes 4, 5, 2. The remaining nodes in the postorder array 6, 7, 3 belong to the right subtree. We then recursively construct the left subtree using pre equals 2, 4, 5 and post equals 4, 5, 2. And the right subtree using pre equals 3, 6, 7, and post equals 6, 7, 3. Once both the left and right subtrees are constructed, we attach them to the root node 1 and return the complete tree. This step-by-step decomposition and reconstruction process ensures that the tree is built accurately and efficiently. Here, we start by defining the tree node class, which represents the structure of a node in our binary tree. Each node has a value, and pointers to its left and right children, both of which default to none. Next, we define the solution class and the method construct from prepost, which takes 2 inputs, the preorder and postorder traversals of the tree. The first check in the method handles the base case where either traversal is empty, in which case we return none since there's no tree to construct. The first element in the preorder list is always the root of the tree, so we create a tree node with that value. If the preorder list contains only one element, it implies that the tree consists of just this single node, so we return it directly. For larger trees, we know the second element in the preorder list represents the root of the left subtree. Using this value, we locate the size of the left subtree within the postorder list. The size is determined by finding the index of the left subtree's root in the postorder traversal and adding 1. This information allows us to partition the preorder and postorder lists into segments corresponding to the left and right subtrees. Finally, we recursively construct the left and right subtrees. For the left subtree, we use the portion of the preorder list starting from the second element up to the left subtree's size, and the corresponding segment from the postorder list. Similarly, for the right subtree, we use the remaining elements of both traversals after accounting for the left subtree and the root. Once both subtrees are constructed, we attach them to the root node's left and right pointers, respectively. The recursion ensures that the tree is built layer by layer, from the root down to the leaf nodes. At the end of the method, we return the root node, which now represents the fully constructed binary tree. Here, we start by defining the tree node class, which is the building block of our binary tree. Each tree node has a value, and pointers to its left and right children, both of which are initially set to null. Next, we define the solution class in the main method, construct from prepost, which takes 2 arrays as input, the preorder and postorder traversals of the binary tree. The method first checks for null or empty inputs and, if any of these conditions are met, returns null immediately since there's no tree to construct. Otherwise, it calls the helper method buildTree, passing in the preorder and postorder arrays along with their respective start and end indices. This helper method is where the actual tree construction happens. At the start of buildTree, we include a base case to handle invalid ranges, returning null when the indices indicate that there's no valid subtree to construct in that segment. If the given range is valid, the algorithm proceeds to construct the tree. First, it identifies the root of the tree or subtree. In preorder traversal, the first element is always the root, so we create a new tree node with the value at the prestart index. If there's only one node in the current range, meaning prestart equals preend, we directly return this node as there are no children to process. Otherwise, we look at the next element in the preorder array, which represents the root of the left subtree. To determine the size of the left subtree, we search for this value in the postorder array. Once found, the size is calculated as the difference between its position and the poststart index, plus 1. With this information, we recursively call buildTree to construct the left subtree, passing in the appropriate ranges for both preorder and postorder arrays. After constructing the left subtree, the algorithm proceeds to build the right subtree. This is done by making another recursive call to buildTree, this time adjusting the ranges to focus on the portion of the preorder and postorder arrays that correspond to the right subtree. Specifically, the starting point in preorder is shifted to skip over the elements of the left subtree, while the end of the postorder range is adjusted to exclude the last node of the left subtree. Once both the left and right subtrees are constructed, we attach them to the root node. Finally, the root node, now representing the fully constructed tree or subtree, is returned. This completes the construction process for the current range of nodes, and the recursion ensures the entire binary tree is built correctly, step by step. In this example, we are tasked with constructing a binary tree from the given preorder and postorder traversals. The preorder traversal starts with 1, 2, 4, 5, 3, and the postorder traversal is 4, 5, 2, 3, 1. The first step is identifying the root of the tree, which is always the first element of the preorder traversal. In this case, the root is 1, so we create a tree node with value 1. Next, we determine the left subtree. The second element in preorder, 2, is the root of the left subtree. To find the size of the left subtree, we locate the index of 2 in the postorder traversal, which is 2. Adding 1 to this index gives us a left subtree size of 3. Using this, we can divide the preorder and postorder lists for the left subtree into 2, 4, 5, and 4, 5, 2, respectively. We then recursively apply the same process to construct the left subtree. For the left subtree of 2, the root is 4, and since there are no more elements for further subdivisions, we create a tree node with value 4, making it a leaf node. After constructing the left child of 2, we move on to its right subtree. The preorder and postorder lists for this subtree are 5 and 5, respectively. Since 5 is the only element, we create a tree node with value 5. This completes the construction of the left subtree of the root, where 2 is the parent with children 4 and 5. Now, we handle the right subtree of the root node 1. The preorder and postorder lists for the right subtree are 3 and 3. Since 3 is the only element, we construct a tree node with value 3, making it a leaf node. With the left and right subtrees complete, we can now visualize the entire tree. The root node 1 has 2 children, 2 on the left and 3 on the right. Node 2 further has 2 children, 4 is its left child and 5 is its right child. The final tree structure is a balanced binary tree with 1 as the root. Now let's look at a simpler example where the preorder traversal is 1, 2, and the postorder traversal is 2, 1. Here, the first element of the preorder traversal, 1, is the root of the tree. The second element in preorder, 2, becomes the root of the left subtree. Since there are no other elements in the preorder or postorder lists, we know there is no right subtree. The left subtree is constructed from the lists 2 for preorder and 2 for postorder, and since 2 is the only element, we create a tree node with value 2 as a leaf node. The final tree structure is straightforward, with 1 as the root and 2 as its left child. This example demonstrates the case where the tree is skewed to one side, and no balancing is required. Finally, let's consider the simplest case where both preorder and postorder traversals consist of a single element, 1. In this scenario, the root of the tree is simply 1, and since there are no other elements in either traversal, both the left and right subtrees are null. We construct a tree node with value 1, and the tree consists of just this single node. In all these examples, the key to solving the problem is dividing the preorder and postorder lists into left and right subtree sections based on the second element of preorder and its index in postorder. This recursive process ensures each subtree is accurately constructed, even in edge cases with single nodes or empty lists. The time complexity of this solution is influenced by the recursive process of building the binary tree and the slicing operations performed on the preorder and postorder lists. To determine the size of the left subtree, we use the postorder.index left_subtree_root operation, which is an O, N, operation because it searches the list linearly. Additionally, the function makes two recursive calls for constructing the left and right subtrees. The size of the lists passed to these calls decreases depending on the sizes of the left and right subtrees. However, each of these recursive calls involves slicing the preorder and postorder lists to create new sublists, which takes k time for a list of size k. These factors together contribute to the overall time complexity of the solution, as we'll explore further. To analyze the time complexity more formally, consider that the tree has n nodes and each level of recursion involves two key operations. First, we perform an O(n) operation to find the left subtree size using postorder.index. Second, we perform slicing operations that cumulatively take O(n) at each level. Since the tree has h levels of recursion, where h is the height of the tree, the total time complexity depends on the tree's structure. In a balanced tree, the height is O log n, leading to a total time complexity of O(n * log n. However, in a skewed tree, the height becomes O(n), and the time complexity increases to O(n²). Therefore, the worst-case time complexity for this solution is O(n²). Now let's examine the space complexity. This is primarily determined by two factors, the recursive call stack and the memory used for slicing. For the recursive call stack, the depth of recursion matches the height of the tree. In a skewed tree, this depth is O(n), while in a balanced tree, it is O log n. As for slicing operations, each recursive call creates new sublists, and these sublists are not reused. The total memory usage for slicing across all recursive calls can reach O(n²) in the worst case. Combining these, the total space complexity is O(n) in a balanced tree and O(n² in a skewed tree. When we compare this solution to a brute force approach, the advantages become clearer. A brute force method would require repeatedly traversing the preorder and postorder lists, resulting in an O(n² time complexity due to redundant computations. While our current solution avoids these redundant traversals, the slicing operations still result in O(n² in the worst case. An improved approach would involve using indices to represent subarrays instead of creating new lists. This optimization eliminates the overhead of slicing, reducing both the time and space complexities to O(n). In summary, the current solution has a worst-case time complexity of O(n² and a best case of O(n* log n, while the space complexity ranges from O(n) in the best case to O(n² in the worst case. When working on this problem, there are a few common mistakes to watch out for. First, not handling base cases properly can be a major issue. For example, if you forget to check whether the preorder or postorder array is empty, this can result in index out-of-range errors or even infinite recursion. To avoid this, always include a base case that returns appropriately when the arrays are empty or contain only a single element, such as a leaf node. Next, incorrect indexing during subarray splitting is another frequent error. Miscalculating the indices for the left and right subtrees can lead to mismatched reconstructions, producing an invalid tree structure. The fix is to carefully derive the indices based on the relationship between the preorder and postorder traversals. Lastly, assuming that all nodes have unique values without verifying this in the problem statement can cause issues. If duplicates exist, your splitting logic may fail because you can't reliably partition the arrays. Always confirm whether the problem guarantees unique values, and if duplicates are possible, you may need additional data structures to handle them properly. Now, let's look at two more common pitfalls. Inefficient recursive calls can be a big problem in this type of question. Specifically, recomputing subarrays repeatedly during recursion can significantly increase the time complexity, often to O(n²), because of the redundant slicing operations. Instead of creating new arrays at each step, you can optimize by using indices to represent the subarray ranges. This way, you avoid the overhead of slicing. Another mistake is ignoring edge cases related to tree shapes. For instance, highly skewed trees, whether completely left-leaning or right-leaning, are special cases that can lead to infinite recursion or incorrect tree structures if overlooked. Make sure to test your solution on edge cases such as single-node trees or highly unbalanced trees to ensure your implementation is robust. To excel in interviews, there are a few key insights to keep in mind. One important pattern is recognizing that the root node always appears first in the preorder traversal and last in the postorder traversal. Leveraging this helps you efficiently identify the subtrees. For optimization, avoid constructing new arrays by using index ranges instead. This reduces memory usage and improves performance. It's also crucial to clarify assumptions with the interviewer. Confirm whether the node values are unique, and discuss how your solution handles edge cases. Additionally, be prepared to explain the time and space complexity of your approach. Highlight that an optimized solution runs in O(n) due to a single-pass reconstruction using indices. Finally, test thoroughly by walking through examples like balanced trees, skewed trees, and edge cases to demonstrate correctness. Related problems you might encounter include constructing binary trees from preorder and inorder traversals, or from inorder and postorder traversals, as well as serialization and deserialization of binary trees and constructing a maximum binary tree. Alternatively, there are other approaches to solve this problem that might be worth considering. One option is iterative reconstruction. This involves using a stack to simulate the preorder and postorder traversal process iteratively, which avoids recursion but can add complexity to the implementation. Another method is to use a hash map for faster lookups. By storing value to index mappings, you can efficiently partition the arrays during reconstruction. While this approach does require extra space for the hash map, it can significantly improve the efficiency of your solution, especially when working with large trees. These alternatives can be useful depending on the constraints or requirements of the problem you're solving. Great job! To summarize, we tackled reconstructing a binary tree from preorder and postorder traversal using recursion. We highlighted key concepts like tree traversal relationships and the efficiency of recursive approaches. Remember to practice similar problems to solidify these concepts. Thank you for watching, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!